We dissected a leaf blower. By taking it apart, we discovered its primary devices were centrifugal pumps, a two-stroke engine, and various pipes and containers.
The turbo machine takes a centrifugal form with a circular-shaped impeller and an Archimedean spiral volute whose radius increases linearly. Unwrapping this entire shape shows us that the mass flow rate coming out from between the impeller blades adds to the total mass flow rate leaving the outlet of the blower. This Archimedean spiral shape allows for the velocity to stay uniform between the impeller blades and the volute casing, even when the overall velocity increased as it moved from the base to the edge of the impeller blades. We see from this graph that radial velocity decreases as a function of 1 over r, and the azimuthal velocity increases linearly along the impeller blades. And when the fluid gets to the edge of the blade, the sum total velocity drops and remains uniform. If designed right, it should match the speed at which it entered the input grill. We see from this graph that the pressure also builds as the fluid moves along the impeller blades and continues to rise as kinetic energy is converted to pressure in the volume.
The specs of this device list the air output velocity as 78 meters per second. As calculated, the Reynolds number of the exit pipe is in the order of 10 to the 6th, indicating turbulent flow. We then use the Reynolds number to calculate the viscous dissipation factor, and then the pressure loss drop using a smooth pipe approximation.
Using the best speed range equations for radial flow, specs from the datasheet we found online for a blower, and approximating the average operating speed is triple the idle speed, we calculate a range of possible pressure change values, 2,000 pascals to 30,000 pascals. Because the max efficiency is 1, we use the efficiency equation to find a better max value of about 3,400 pascals. The max pressure change if this were an axial flow blower would be about 800 pascals, which is double what the losses from the pipe would be, and the max efficiency is only about 23%. The centrifugal blower has a minimum 58% efficiency and has a minimum pressure change of 5 times the losses, so we see that it is the better choice to achieve our engineering outcome of creating a large pressure difference that forces the air out of the pipe at very fast speeds.
Taking off the intake grill in the back, we see that the reel for the pull cord used to start the engine is mounted on the inside. This pull cord engages a mechanical connection to the engine's flywheel that causes it to start spinning. Continuing to take off the casing for where the handle is explains how the trigger mechanism works, and as seen here, it releases a catch that is related to the throttle control of the motor.
There are 2 impellers in this leaf blower, the orange one we examined earlier and the gray flywheel with an opposite blade orientation. The 2 are connected by an axle. The flywheel's main purpose is to cool the engine by pulling in ambient air and circulating it around the hot components.
On the rear side of the leaf blower, we see the carburetor, which controls the proportions of fuel and air that enter the engine independent of the output being produced by these moving parts.
We can use conservation principles to determine how the pressure drop through the throat of the venturi of the carburetor is related to the velocity of the fluid passing through it. Now, we can use conservation of mass to determine that the area at the throttle valve times the velocity of the fluid passing through the throttle valve is equal to the area at the throat times the velocity of the fluid passing through that. So, A1V1 is equal to A2V2. Since we know that the area of the throttle valve is greater than the area of the throat, that means the velocity passing through the throat must be greater than the velocity passing through the throttle valve. Now, we can rearrange the differential form of the Bernoulli equation into the following relation, which relates the difference in pressure between the throttle valve and the throat with the difference of the velocity at the throat squared minus the velocity at the throttle squared. Since we know that V2 is greater than V1, this gives us a positive value here. A positive value here means that there is a lower pressure zone at the throat compared to where the throttle valve is, which acts as a way for the fuel to be sucked in from the fuel reservoir, mixed with the air over here, and deliver a mixture of fuel and air into the engine, which is attached after the carburetor. Now, we can plug in some numbers into this situation. We found that the diameter of the throttle valve is approximately 1.5 centimeters, and we approximated that the diameter of the throat is about a third of that, meaning that we get a velocity through the throat that's 9 times the velocity through the throttle valve. So, using this equation that we found earlier, we can plug the numbers in and find that the pressure difference is about equal to 40 times rho times V1 squared, which is an enormous pressure difference generated from a relatively small change in geometry.
Next, we looked at how the two-stroke engine actually powers the blower. Fuel, air, and a bit of oil come in through the intake valve from the carburetor and fill the combustion chamber. When the spark plug fires, it ignites the mixture, forcing the piston down. You can see how the piston is connected to the crankshaft through the connecting rod, which converts that up and down motion into rotation. Next as the piston moves back up, it pushes the exhaust gases out through a one-way exhaust valve, while also drawing fresh mix of fuel, air, and oil for the next cycle. This simple up and down motion is what keeps the crankshaft and the impeller spinning continuously. Next, we ran some numbers. Each cycle produces about 13.6 joules of work, giving a torque of 2.16 Newton meters at the crankshaft. At full speed, the shaft power is roughly 1.9 kilowatts, with a thermal efficiency of 0.361.
Thanks for watching!